So this first slide really shows one of the major issues with soil acidity in that it's highly variable, as the previous presenters pointed out. This is our record low pH in Montana, pH 3.8. You can see nothing grows at 3.8. And then right on the edge of that is pH 5.1, where the crop looked essentially perfect. The scary thing to me is pH 5.1, based on our research, is going to be in the fours within just a couple years, and will begin to look like this probably in a decade or so. If you do have any questions, throw them in the chat. If you have any questions after the fact, feel free to email me at this email address, or always feel free to give me a call. So I would like to gather a little bit of information from you all, and please do this in the chat. I'd like you to enter 1 if you found some low pH in some portions of your fields, meaning either your field if you're a producer or your client's fields if you're a crop advisor. Enter a 2 if you haven't seen anything that low, below 6, and then 3 if you're really not sure. And so feel free to fill up the chat. I'm seeing a lot of 1s there. More 1s than anything. Okay, that gives me a flavor. You know, just 5 years ago in Montana, if I'd asked this question, we'd be getting a lot more no's than yeses, and that seems to have really changed just in about 5 years. Thanks, everyone. Second question, a few more options would be, what are you or your clients doing? Put an A if your clients, really aren't that concerned. Maybe they're in a higher pH zone. Put B if they're concerned, but they're not really doing much. And then I have C through I there. Basically, there's some specific changes that you or your clients can make, from prevention to seed place phosphorus, like Brian just mentioned, or liming, like Chris and John mentioned. So I'm seeing some multiples, C, range, B, C, D, G, H, not F, so not including perennials. Another C. All right, so it looks like kind of a range, B and C. Some are not concerned, some are soil testing. Pretty good range. And that's kind of what's happening here. There's a lot of actually concerned people, but the expense of doing most of these are actually fairly high. So changing a rotation is not always conducive to profit, for example. Making changes to fertilization in a high protein hard red wheat zone is not always the best thing to do. Lime is expensive. We don't have water treatment plant lime. We don't have many quarries here. And so pretty much beet lime is the only choice, and it's far from the low pH zones. Thanks, everyone. So what to do about soil acidification? I talk about MAP, and so mitigate with lime, adapt, which is what Ryan asked me to talk about today, which means either seed place phosphorus or planting tolerant species, or prevent, such as increasing fertilizer end use efficiency, changing the nitrogen source, maybe including legumes in rotation, or planting perennials, and finally leaving more stubble in the field. Again, today I'm talking about adaptation, but on my website I have quite a bit of info on liming and prevention. So as Brian mentioned, seed place phosphorus can be very effective at increasing yields in these low pH zones. Here I have a study that my colleague Rick Engel did a few years ago on durum wheat, where he applied no phosphorus in a pH 4.4 soil, a lot of phosphorus, 90 units. And then you can see really visually the durum without phosphorus and with the seed place phosphorus looked and yielded dramatically different. So when we look at the results from that study, here what I've plotted on the horizontal axis is the units of phosphorus. And we used triple superphosphate because we didn't want to have an additional variable of nitrogen in the study, or nitrogen rates. And then we plotted grain yield on the vertical axis in bushels per acre. This flat line is our lime treatment. So we brought the soil up to pH 6.1. When we limed, you can see it didn't matter how much phosphorus we applied, the yield was always about 46 bushels per acre. But when we didn't lime and we didn't add any phosphorus, we only got about 23 bushels per acre. When we limed, or when we added phosphorus, just a fairly small amount, something that's fairly typical for our direct seeders to put in with their seed blend, somewhere around 15 units to maybe 30 units, we saw dramatic increases in durum yield. And then by the time we got up to 60 units of phosphorus, we had essentially maximized the yield and had the same yield as our lime treatment. So as Brian mentioned, we can see some dramatic effects of seed-placed phosphorus. However, on another site that was just slightly higher in pH, this one was 4.8, we saw essentially no benefits of phosphorus. So the question here was that just because it was a low yielding site? Maybe it was more water limited. Likely in Montana it was more water limited. Or is that slightly higher pH meant that this wasn't a site that was affected as much by low pH and aluminum toxicity? We don't know. Something really dramatic to me, though, is that both of these sites had very high phosphorus levels, way above the critical level. And so if you just used phosphorus as an indication of should you add any phosphorus, you would say definitely not. But we saw this dramatic effect even with high phosphorus. What about economics? So we ran some economics on that same study at the pH 4.4 site. And as you could probably expect, we saw dramatic benefits in net revenue in dollars per acre. So this is the yield, and the red dashed line is the net revenue. It looks like probably somewhere around 30 units would be about as good as we'd get, maybe a little higher at 60 and no better at 90. But on that other site, adding phosphorus actually decreased net revenue. So what to do? I'd really recommend field strip trials before you spend a lot of money on phosphorus. See if this works for your farm or your client's farm in a few small spots before you go, wall to wall. Another adaptation strategy, as you're probably aware, is to adjust your crop or adjust your client's crop. So this is work done out of Idaho many years ago, but we think we see some of these same effects on different crops from pH. So here I plot soil pH on the horizontal axis, the maximum yield attainable up to 100% on the vertical axis, and then the responses of different crops. So a high tolerant wheat basically did not really show much of a drop in yield, even in the pH 4s. But barley shows a pretty dramatic drop in yield as pH goes down. A low tolerant wheat, even more dramatic, and then all of the legumes start having a yield drop off somewhere in the mid 5s, not necessarily because the crop is intolerant. We think these crops actually, we've seen them be very tolerant as long as the nitrate levels were high in the soil. We think this intolerance is due to the rhizobia, which are fixing nitrogen. So most of these crops are going to show nitrogen deficiency at low pH. You can also adjust your variety. So this is a study that was done in one of our lowest pH zones in Montana called the Highwood Bench in Choteau County near Great Falls, Montana. We had pHs in the upper 4s. We then limed half of those and got pHs in the upper 6s. And what I've plotted here is wheat yield on the vertical axis for 3 varieties that have the aluminum tolerance gene. Alum from Washington State and Duclair and Lanning that are used here in Montana. And then 6 varieties that do not have the aluminum tolerant gene. In that low pH zone, as you'd probably expect, the varieties that had The aluminum tolerant gene generally did better than without, but not always better. We have one under testing that did pretty well, and Duclair that has the aluminum tolerant gene really didn't do better than some of these other varieties. What about at higher pH? So at higher pH, you can see that the aluminum tolerant varieties actually in some cases did worse than the no aluminum tolerant gene varieties. And then really importantly, as the previous presenter Brian showed, most of these fields have both low and high pH zones. You're probably not going to plant aluminum tolerant variety just in the low pH zone and a high and something else elsewhere. You're going to plant it across the whole field. So really, it's probably these averages that are most important. And interestingly, these aluminum tolerant varieties did about the same as some of the non-aluminum tolerant varieties. Some of these non-aluminum tolerant varieties did not have a very good average, but what we've decided is probably the varieties that are well adapted to your soils and your climate, your weather, probably, which these are, probably are going to do maybe as well as the aluminum tolerant varieties. We especially like Lanning because it's so consistent between low pH and high pH. Another adaptation would be to plant perennials. Perennials can slow or reverse acidification based on work done by Mark Liebig at Mandan, North Dakota. So here, over a 5-year study, he plots the soil pH in the top 2 inches for continuous spring wheat. You can see the pH gradually goes down, and then he also planted a range of perennial forages from legume grass mixtures to straight grass. He fertilized them all the same, 60 pounds of N per acre, and notice the perennial forage pH by the end of the study had actually bumped up the pH compared to continuous wheat by about 0.6 units. So pretty dramatic difference if you have the patience and you have a swather or you have animals to take advantage of that perennial forage. One question I got was, well, if annual crops don't do well in low pH, maybe forages won't do well either. Notice this pH wasn't dramatically low. So can perennial forages establish and do well in low pH environments? This is a photo that I took in 2017 of a low pH site near Bozeman, where we had pHs as low as 4.1 and places where nothing was growing. This field back here, this is actually just grass that's going dormant, but this nearby field is all barley. And so you can see there's areas where essentially nothing is growing. So I suggested to the producer that he plant a mixed grass. And so he came back in 2018, planted 6 varieties of grass over that entire field. And what you can see in 2020 was really good establishment. This is about taken from the same spot. You can see junipers here that match these junipers here. And what I asked, well, what 6 species did you plant? He planted intermediate wheatgrass, meadow brome, both of which were well established on this site. He planted slender wheatgrass, which we only found about 5% of, some pubescent wheatgrass, only 1%, and then probably the 2 most expensive grasses in there, blue bunch and Indian rice grass, we couldn't find 1 plant. And so we think these 2 varieties, intermediate wheatgrasses and meadow bromes, are quite acid tolerant. If you want more details on varieties that we have found in Montana to do well on low pH soils, you can go to my webpage, landresources.montana.edu, and go to the soil acidification page on there. So to summarize, cropland soils are becoming acidic, largely due to N fertilization. I would highly recommend that you identify whether fields have a problem now to slow or prevent acidification with sound management. Seed-placed phosphorus can counter the aluminum toxicity. I'd recommend planting adapted species and converting potentially, if this can work for your systems, to perennials to slow or reverse the trends. And again, if you want additional information on soil acidification, you can go to my website here. We have a number of presentations, 3 fertilizer fact sheets on acidification, and a number of soil scoops. And with that, any questions?